Alrighty, so we are now recording. Alrighty, so so like I said, we're going to review a little bit about what WISE is, and that is a WISE image in the background. It's one of their later most recent releases. I think it's pretty cool. So just an outline, like I was just saying, we're going to do an introduction to WISE. I'll go over the archive interface, and then I'll take questions. The WISE website for historical reasons, the Education and Public Outreach portal is at Berkeley, but if you just Google WISE and Berkeley, there is another program called WISE at Berkeley, which is not this mission. So you do need the SSL in the URL, or you need to actually read the Google results and not just click I feel lucky. So in terms of the overview, WISE stands for Wide Field Infrared Survey Explorer, and it's an entirely NASA-funded mission. There's no international participation in this mission, and it's something called an Explorer class, which basically means it's a small mission. I mean, in your mind, you can think of really big missions involving multiple nations and taking years, and then you've got other shades of gray all the way down to Explorer class, which is basically the launch vehicle, 2 guys, and a roll of duct tape. I mean, it's really, really very low budget. So this is I think the smallest kind of astronomy mission that NASA has. It covers between 3.5 to 22 microns using just one instrument that has 4 cameras inside. It observes in all 4 of those channels at once, 3.4, 4.6, 12, and 22 microns. Sometimes those are referred to as WISE 1, WISE 2, WISE 3, and WISE 4, or W1, W2, W3, and W4. It was launched from Vandenberg here in California in December 2009. It had some cryogen on board that ran out a little faster than anticipated in only about 10 months. It did a little bit more just by passively cooling, and then it turned off in February 2011. Now, technically, the spacecraft is completely functional. It's just in hibernation, and it could be reactivated if there's money. There seems to maybe be some movement on that front, so hopefully we'll be able to keep WISE going. So it is, of course, a survey mission. What that means is it looked at the whole sky. Other missions you may be familiar with, like Hubble or Spitzer or Herschel, those are pointed observatories. So they have a proposal call. Each time astronomers ask for at least 5 times as much time as there is actually physically available on the spacecraft. And so there's a committee that gets together and decides what are you going to look at and for how long. Whereas with WISE, it just looked at the whole sky. It didn't dwell in particular in any one position. However, it is in something called a sun-synchronous polar orbit. I have more movies on that in a second, but that little animated GIF on the right is showing you what a polar orbit looks like. And the Earth graphic underneath is not terribly clear, but it looks to me almost like this is actually at the sunrise-sunset terminator, which is where WISE lives. WISE orbits at the same cadence as sunrise and sunset. So it's in perpetual sunrise or sunset. And IPAC here at Caltech is the Center for WISE Operations and Data Processing and Data Archiving. So this is just a short history of WISE. It was initially proposed in 1998. It lost out to some other small missions in 1999. They went back and reproposed in 2001. They got funded in NASA speak. There's phases of a mission. There's phase A to phase D. You don't need to know the details of that. You just need to know that it's been in serious development since 2002. That's really the relevant part. And it launched in December 2009. That's what the actual spacecraft looks like. And this is an actual picture of it. Look at how small that spacecraft is compared to those people. The mirror diameter here is only 40 centimeters, and so the telescope and therefore the spacecraft is really small, especially compared to other missions like Herschel or Spitzer. Spitzer's telescope is 85 centimeters, so it's larger than that, and Herschel's telescope is 3.5 meters, so it's huge compared to WISE. WISE is actually a pretty tiny little spacecraft. It goes with the fact that it's Explorer class. There you can see it inside the telescope or the rocket fairing. It looks kind of lonely inside the rocket fairing in there because it's a very small mission. So the timelines, I've already covered this in high-level detail. It was launched in December 2009. They did a whole bunch of startup work, and then they finished their first pass on the sky in July 2010. They ran out of cryogen at the end of September 2010. They did some what they call post-cryo, in other words, post-cryogen. They did some continuing survey in that, and they've had a series of waves of data releases. The most recent one well, the most recent one that we're going to be working with here is the All Sky data release, which was last March. There were some more incremental releases having to do with the 3-band cryogen data and the post-cryo data. Those are still, a preliminary release was made and they're still refining it. They just recently got money for the All WISE project to co-add all of these WISE data, and they're hoping to release that late next year. So this is a fairly technical slide, but the movie is why I have it here. So remember, this is a polar orbiter. So if you imagine the Earth is the tiny little dot in the middle there, this is how WISE is filling up its coverage of the sky. So it's looking out on each one of these orbits, and each orbit moves just slightly a little bit with respect to the previous orbit. So a single field of view is 47 arc minutes, which is huge, and as it's going along, it's tiling together a strip of images, and then the next orbit is offset just a little bit, and after many orbits you get complete coverage in the center of where you started over here. Now you can see how there's a lot more frames at the poles than at the equator, and that comes from the fact that it's a polar orbit. So in every orbit it's going to go look at the poles, but on the equator, it's only, or the ecliptic rather, it's only going to see it's going to have the minimum number of frames that are possible. And it turns out the moon also matters. So what the statistics up here are telling you is that at minimum there are 8 frames per position on the sky per band, but more typically there are 14 frames per position per band. And that's because the moon gets in the way, and so does something called the South Atlantic anomaly. We can talk about this later, but basically it's a collection of charged particles, part of the Van Allen belts, basically above the South Atlantic, and it's really hard on spacecraft, and so spacecraft really need to turn off when they're going through the South Atlantic anomaly. So between the SAA and the moon, there's some data losses. It's not a complete coverage like the movie here, but it is pretty good coverage even on the equator. So this is just sort of the high-level summary of that. Here's a still version of that, and basically the moon and the radiation belts matter, right? You're not going to get absolutely complete coverage on the equator or in the equatorial region because of that. This is a map of the galaxy, and this movie is showing you how they filled out coverage of the sky. So that coverage is, of course, in ecliptic coordinates, and then the image in the background is galactic coordinates. They've transformed the ecliptic coordinates in the movie we just saw into covering the galaxy. So you can see, I'll play it again, you can see on the right, as time goes on, it's filling up the coverage of the sky. So you can see some parts of the galactic plane get pretty good coverage, and there are some parts of the ecliptic plane, which goes like this, that don't get very good coverage. Okay? So how does WISE fit in? If you've played around with infrared data in general, it might seem like we might have a lot of space-based infrared observatories right now. And it's true, we do. But WISE really does fill a specific niche. So there's 3 big infrared missions that are flying right now: Spitzer, Herschel, and WISE. Spitzer is 85 centimeters. Herschel, like I said, is 3.5 meters, and WISE is only 40 centimeters. But look at the wavelength coverage. Herschel needs that big telescope because it's looking at very long wavelengths. We'll talk more about spatial resolution in a second, but that's why Herschel needs such a big telescope, is because it's looking at very long wavelengths, 50 to 700 microns. Spitzer observes between 3.5 and 160 microns, and you might justifiably ask, well, wait a minute, isn't there some overlap in the wavelength regions between WISE and Spitzer? Well, Spitzer's a pointed observatory, and WISE does the whole sky. That's really the huge difference, is that WISE does the whole sky. It's not going to do some particular regions in as much depth as Spitzer, but that's the pluses and minuses here. Spitzer launched in 2003 and WISE launched in 2009. Their orbits are very different. We can talk more about that in a later talk, but Herschel is at a Lagrange point. WISE, like I said, was in the sun-synchronous polar orbit, and Spitzer is actually in an Earth trailing orbit. It orbits the sun just like the Earth does. All of them had cryogen to help keep themselves cold because they're infrared telescopes. If you try to observe in the infrared with a warm telescope, it's like trying to observe in the optical out of a telescope made out of those fluorescent light tubes. Not very effective. So they all carry cryogen on board to try to cool themselves down. Spitzer ran out, WISE went out, and Herschel will be running out beginning of next year probably. So Spitzer's on an extended mission right now. Herschel, it's not possible to do an extended mission because the telescope's going to be ambiently warm up enough so that you can't observe their bands. And like I said, WISE is in hibernation now. Both Spitzer's and WISE archives are hosted here at IPAC, and so they have very similar look and feel. So once you master the WISE archive, hopefully the Spitzer archive, and for that matter the Planck archive and some other archives here, will not be as intimidating as they might be because it has the same look and feel. So I did mention we were going to talk a little bit about spatial resolution. Whenever you're planning an all-sky survey versus a pointed observatory, there's always a trade-off between spatial resolution and the survey depth or integration time. So if you got money to do a survey that covers the whole sky, typically you really don't have resources to stare at just one region. You really need to get through your entire survey as fast as you can. Survey depth, meaning how long you stare at one particular part of the sky, in other words, how faint you can get. If you stare at one space on the sky, you're going to see fainter things. But survey telescopes really don't have the luxury for that. Pointed observatories can stare at the same piece of the sky for hours, up to months at the same piece of the sky, and certainly some telescopes have. But sky surveys really, you know, if you get the money to do the survey, you're going to run out of time. So you need to finish the survey. You can't stare at one place for too long. So typically, if you're covering the whole sky, again, just for logistics reasons, you probably need a wide field of view. And what that means is typically your spatial resolution is really not as good as other telescopes that are pointed. And it turns out, once you get into the physics and the optics of it, it is intimately tied to the size of the telescope, because the spatial resolution is going to go as 1.22 lambda over d, where lambda is the wavelength of your light, and d is the diameter of your telescope. So in other words, the key point here is that if you observe at longer wavelengths, you're going to get worse resolution. And if you have smaller telescopes, you're going to get worse resolution. That's just the way that it works. So here, two examples: the Palomar Observatory Sky Survey. That's a pretty famous survey, but it's actually not done with the Palomar 5-meter. It was actually done with a 48-inch Samuel Ocean telescope, and the 5-meter is used for pointed follow-up observations, originally for a variety of things, including POS, but it's not used as a survey telescope because it has a pretty small field of view because it's a 5-meter telescope. Spitzer is 85 centimeters and Herschel is 3.5 meters, but WISE is only 40 centimeters, and that, again, is all bound up in the fact that Spitzer and Herschel are pointed observatories, but WISE is a survey. So here's some images of the same region of sky, the Eagle Nebula. Up here is the Hubble image of the Talons. In the background here is the 4-color Spitzer image, and the color scheme has been chosen here such that blue is the short wavelengths and red is the long wavelengths of light. That's the same region there, the Talons from Herschel. Now, what was the reddest light in the Spitzer image at 70 microns is now the bluest light for Herschel. So it has a more ghostly feel because it's got more of those blue tones, but that's because it's observing at even longer wavelengths. There's the 2-color WISE image of that same region, and you can see it is distinctly blurrier than those other telescopes. And that's what I mean by poorer spatial resolution. The WISE resolution, spatial resolution, is really not that high, but it covers the whole region, which is critical. So here's a real-life example of spatial resolution. My science research is to look for young stars, and so up here is an image of a particular thing that we thought was a point source in all 4 WISE bands at 3.5, 4.5, 12, and 22 microns. And you can see that the spatial resolution at 22 microns is far worse than 3.5. This is the same chunk of sky, but with the steadily worsening WISE PSF with wavelength. But then when you actually look in JH and K, or in the Palomar Sky Survey, or even in Sloan data, you can see that's distinctly not a star. It's actually a little elliptical galaxy. So the issues of spatial resolution can be, and hopefully will be, a talk unto itself, but I did, specifically in the context of WISE, want to call your attention to the fact that the spatial resolution is going to be bad compared to what you're used to. It's not going to be as good as ground-based observatories or surveys like POS. It's not going to be as good even as Spitzer. You have to worry about this because the spatial resolution is just not as high as you might be expecting. So be sure you know exactly what wavelength is being quoted when you're looking up resolution. The actual quoted resolution for WISE, the 4 bands of WISE, are about 6 arc seconds for the shorter bands and 12 for the longest bands. And that's not the same as pixel size. There's a bunch of stuff on the NITARP wiki if you want to look some more and think some more about issues of spatial resolution. Like I said, hopefully I'll do another one of these in the future. So one of the things that WISE is really famous for is asteroid hunting, because asteroids, they're heated by the sun and they thermally glow. So their emission peaks between 12 and 25 microns. So WISE is just really good at finding these rocks. They have found more than 158,000 asteroids and comets, and just in the main belt alone, 34,000 asteroids. So it turns out that when they're close, since you're taking several consecutive exposures, you can see them move. You see those green dots? That's the same asteroid moving as the telescope was taking a series of images here. There's another trail blown up here. There's another trail. That one's so close it's actually smeared. So lots and lots and lots of asteroids. This movie shows you exactly, it's a catalog of everything that WISE has discovered. So you can see the orbits there are the planets, and you can see that WISE is sweeping out coverage of the sky. The blue dots are, well, planets. The black dots are the new things that they found. The green dots were the known near-Earth objects. The red dots are completely new near-Earth objects that they found. The turquoise dots are known comets, and the yellow squares are new comets. So they found lots and lots of things. And you can see one of the things I really like about this movie is that these things are all moving. So even though that line is fairly sharp as the coverage of the sky, as WISE continues to sweep out coverage of the sky, you can see back here it's already smeared out because these things are following Keplerian laws and rotating around the sun differentially. So that line smears out as it's looping around here. I think it's almost done. I think it stops when they had the complete coverage of the sky. We will be covering, there was enough interest, I think, that we're going to be covering the WISE data specifically in the context of asteroids and comets in a later webinar. So I'm not going to cover it here just because, there's lots of other things that you can do as well, and because there's enough interest in moving objects that we'll cover it later. So these are just some of the statistics. As of the last time I got a number out of them, there was 20 new comets, 33,000 new asteroids, 134 new near-Earth objects, as well as Earth's first Trojan, which is really cool. If you think of the Trojan asteroids, there's a clump of asteroids in Jupiter's orbit before and after Jupiter. It has been thought for years that Earth might have Trojans because Mars has a few, but it was really hard to find them because they're so close to the sun. But WISE found one. It has a really funky orbit, and that's really cool, but that's a separate conversation entirely. And then this is I think the last slide that I have here is just giving an inventory of what was known before WISE, which are the rock-colored things, sorted by size. What was thought prior to WISE, the inventory of things that, for example, we might have to worry about hitting us, is out here, is those turquoise colors. But then the new predicted total are these green symbols based on what WISE saw. So in other words, there's far fewer rocks near us than we had feared, which is good when it comes to planetary protection issues. So this is actually my last slide. So WISE was a survey mission, and so part of the deal was that IPAC was going to generate complete images and catalogs for the whole world to work with, you guys as well as professional astronomers. And they're all available, and it's great. The data are so rich. We're going to be mining this for years and years, probably decades. But you have to remember that there are over 2 million frames that went into this, and they got turned into 18,240 FITS image sets, but over 563 million sources. So the computers are doing a lot of the work here. And while there are people involved, they cannot catch everything. They just can't. The computer's doing the best that it can, but it has to handle a huge variety of data. Isolated point sources, clumpy point sources, sources with high background, moving objects. It's doing the best that it can, but it's not going to be perfect. Just because the computer says it doesn't mean it's right. So if you remember only one thing from this talk, besides the fact that WISE exists and the catalog exists, please, please, please remember to read the documentation. Pay attention to what the computer is telling you about how confident it is about the point source. And I cannot emphasize this enough. Go and look at the images. Trust me, it's going to save you a lot of pain in the long run. Professional astronomers are making these same mistakes. They're publishing papers saying, oh, I saw all these sources. But if you actually go and look at the images and pay attention to the data quality flags, you'll see that those astronomers probably did a lot of work that they could have avoided had they looked at the images to start with. So I cannot emphasize that enough. So let's see. Let me pause here for questions about WISE, the mission as a whole.